Welcome back to ECE 441A, 541A. Our exam is Friday, and hopefully we'll have a few more filled seats on Friday. There is a little bit of extra material now on D2L talking about what happens or how do you address a polynomial that has a variable parameter inside it in terms of computing the Ruth array. But you've done that, I think, on homework, but this is another illustration. And it's not 50 minutes, it's half that. It's about 23 minutes in terms of length. Homework number 5 is due today. You should be familiar with the practice exams that are available on D2L, and lab number 2 is due a week from Monday, I think, something like that. And I didn't put up here no class a week from Friday, which is the 28th on Engineers Breakfast. So that's something that I've been announcing and forgot to announce today. Today what I want to do is just remind you of the exam number 2 process, and then we'll talk a little bit more about steady state air and system type. I think I've in passing mentioned something about system type, but I want you to become more familiar with that or comfortable with that. But system type really is keeping track of how many integrators you have in your forward path in your block diagram. The process for exam number 2, what you are allowed, you can now have 2 sheets of notes if you so desire, front and back. And if you want to bring a Laplace transform table, you're bringing it. I'm not furnishing it. That apparently wasn't that clear last time, but I don't know that that was that critical. It may not be that critical this time, but if you want it, it's available to you, but you need to bring it, and something to calculate and write with. What's not allowed are the obvious textbooks, class notes, computer, and cell phone, and neighbor. I didn't put that in there, but I should make that clear. Questions on exam number 2, process. And you have examples to look at on D2L to get you up to speed on what you might be expected to do on Friday in exam number 2. Let's start based on a question that I had after class last time, and it's connected really with today's class. What comes to mind when you see 1 over S? So I heard a couple of things. I heard 1, and I'll have to interpret that a little bit or filter that a little bit. And I also heard an integrator. So why are we thinking 1 and an integrator? Those aren't the same, but they both come to mind possibly when you have a 1 over S. And that 1 over S then can be vague in terms of what it means. It can mean both. And the reason it can mean both can get or can be confusing, but in your system, 1 over S, if it's a signal, then it's 1. If it's an operator, if it's inside a block, then it's an integrator. And you could have a 1 over S going into a 1 over S block, which means you're integrating a constant, and you'll get out a waveform whose Laplace transform is 1 over S squared, and in the time domain that's a t, or a ramp type input. So this 1 over S, what comes to mind, you have a couple of different possibilities. And the first one that I think I heard was if I had 1 over S, oh, I can think of that as 1, as a constant, as a unit step. And this is starting actually at time equal to 0. That's for t greater than or equal to 0 when we have this one-sided Laplace transform. That's 1 over S. And in this case, this 1 over S corresponds to a signal or a waveform. And in this case, since the coefficient upstairs or up top is 1, it's actually a unit step, which is where the 1 comes from in the time domain. Another possibility as you indicated is maybe when you visually, or when you see that 1 over s, maybe you're putting it inside a block to be in operation. And in that case, this operation in the time domain looks like an operation, and in this particular case, this operation, since it's division by s, is an integral operator, or an integral operation. And what we are going to find as we move through the class is introducing integrators can really be beneficial to our system, but there's a trade-off. If you put a pole at the origin, how stable is that pole? Marginal, isn't it? It's on the stability boundary. So why are you putting things that are marginally stable into your system? Why would you want to introduce an integrator? Well, they are going to increase your system type, and they are going to improve your steady-state accuracy. It's this trade-off between steady-state accuracy and transient behavior. So using pure integrators can be very beneficial when trying to improve steady-state accuracy, or that is small steady-state error. Which leads us into what I want to talk about today, which is this topic of steady-state error. We quickly went through that, but let me now try to provide you with a little bit better intuition or insight into how the steady-state error could be related or is connected to the system that you are dealing with or that you're playing. Let's look at a fairly general block diagram. Let's say that we now have G sub C of S, that's our controller, which now influences our plant. Those two are in the forward path and they are in cascade, and hopefully I left them enough room to put all of this together, because you won't want to be cutting your paper vertically and splitting it and adding. So preceding this summing junction, let me put in another gain block, or it could even be a transfer function. Let me call it G sub F. And then we have our signals, our output signal, our input signal, and maybe to help us, we might call this R sub 1 of S, since typically we don't have that preceding transfer function in front of our summing junction. But in general, let's assume that we have one. And we could also have some feedback dynamics. A transfer function that now might be adjusting, possibly relative to frequency content, and that's why I'm calling it feedback dynamics. It may be more than just a constant. And we have a negative and a positive. And that's our generic, or a fairly generic, interconnected block diagram. We have our controller, our plant, our feedback dynamics, and possibly even a feedback or a feed-forward gain in front of the summing junction. Now, if we are interested in the air signal, that could be somewhat vague. But let's define our air signal to be the difference. Maybe we want our output Y to actually track our reference input R. And for that reason, then, let's call our air R of S minus Y of S. Is that signal anywhere present in the block diagram? Do we create that signal anywhere in the block diagram directly? No. We could if H was 1, H of S was 1, and G of S was 1, then our air signal would actually be the output of that summing junction. Is that clear? But in this generic block diagram, we don't have that air signal physically available to us as a waveform anywhere in that block diagram. And we may want to know how is the output actually tracking or following the reference input. And we can find this relationship. What is Y in terms of R sub 1? What's the output in terms of R sub 1? Cheer 2, isn't it? If we have now, in terms of our G, if we expand that to be G sub CG. So we've now modified our cheer a little bit. It's now G sub CG over 1 plus G sub CG H. And that will give us T sub 1, or the transfer function between R sub 1 and Y. Or Y is now, let's say, T sub 1 of S times R sub 1 of S, with T sub 1 of S equaling, from cheer 2, G sub CG over 1 plus G sub CGH. And you are very comfortable doing that, and now you essentially have the transfer function between R and Y, because you know how R and R sub 1 are related in this block diagram. R sub 1 is the output of the block G sub F fed in with R. And so now we know that R1 is G sub F R, and we can now plug that R1 in the earlier expression to obtain the overall transfer function. Y of S is now T sub 1 of S, G of S, R of S. Or we now have G sub C, G, G, F over 1 plus G sub C, G, H, all times R of S, and this now we might call our transfer function T of S. And now that we have this expression for Y in terms of R, we can come back and apply that or use that in this air signal expression. We can now write down that our air, E of S, if that's R of S minus Y of S, I can now have an R of S in common with both of those terms on the right, and I can factor it out. I have 1 minus T of S times R of S. And if I want the steady state air to tell me something about the accuracy of this system in terms of its tracking capability, air steady state is now the limit as t goes to infinity of E of t, where E of t is the inverse Laplace transform of capital E of S, or that's now the limit as t goes to infinity of R of t minus Y of t And that's, by the final value theorem, the same as the limit as s goes to 0 of s e of s, which is the limit then as s goes to 0 of s times 1 minus t of s r of s. And if we plug in r of s as 1 over s, we can maybe get those s's to cancel, and we're looking at the expression being evaluated when 1 minus t of s for s going to 0. And that will give us our error in that particular block diagram. Let's look at what this error signal might look like for several different plants or several different systems. And let's go ahead and use the plants that we've played with before, find the air steady state using plants from earlier lectures. Because hopefully those we know we've shown those to be stable. So in this case, let's simplify our block diagram, and if we have a controller, we will simply combine it in with our plant G. Here's now y of s, r of s, and now we can think of our air signal explicitly existing in our block diagram. And let's go ahead and examine the steady state air for a unit step. And if it's not a unit step, how do we change that? If it's a constant, how would we change r of s? If little r of t was a constant a, how would we write capital R of s? That would just be an a, right? Meaning, if you don't memorize all of these formulas necessarily, because somebody might say, oh, I have an input that's 2. And you go, well, that didn't work with my formula. Well, that's maybe because now we have a 2 over s instead of a 1 over s as we follow this down. But for us, let's just keep with the unit step. We're trying to focus on the behavior, not necessarily the magnitude of our results. Our air signal, E, since it's in the block diagram, we can do some block diagram algebra directly or obtain that air signal from the block diagram. We have r minus y, and now if we see that y is a function of E, we can now say that y is g of s, e of s. And I can now take both e of s terms to the left, and the transfer function now between the air signal and the reference input is 1 over 1 plus g of s. And let's now look at this, or what happens to this air for different possible plants, G. For example, let's say that we have our A system, which from a previous lecture, G of s was k sub 0 over tau sub 0 s plus 1. And for this case, let's say that k sub 0 is 10 and tau sub 0 is 1. How many integrators or poles at the origin exist in this G of s, in this plant? How many poles do we have at the origin? We don't have any, do we? So this is a type 0 system. And we'll come back to that in a little bit. And is the closed loop system stable in this system? Do you remember? How would we check that? So if we wanted to check closed loop stability, what are we wanting to be true? We want to look at the closed loop transfer functions, denominator polynomial, find those roots. You could do that with the root array and see if all of the roots are in the left half plane or that you don't have any sign changes. And that would then allow you to conclude that your system is stable. In this case, the closed loop system is stable. You have tau 0 s plus 1 plus k naught, and this was a pole at minus 11, if I remember right. And that's in the left half plane. So this closed loop system was or is stable. It was from before. And now let's apply the final value theorem to find the steady state error. And we have our expression for E of S. Air steady state is now the limit as S goes to 0 of S times E of S, which was 1 over 1 plus G of S times R of S. And again, if we had something other than a unit step, that would be an A if it was a constant input. And so our error would be adjusted by the magnitude of our reference input, is what I'm trying to indicate there. We can simplify this a little bit. This S cancels that S, and we now can look at the limit as S goes to 0 of 1 over 1 plus G of S, or that now becomes 1 over 1 plus, we replace S with 0. S equaling to 0 is at what frequency? If S is equal to 0, what frequency am I talking about? 0 hertz, which is DC, right? So this G at 0 for this system is our DC gain. And you can see then that the DC gain, and actually that's quite common to just call that K sub P, and it's defined then in the book as the position error constant. And do you see the relationship between that error constant, the position error constant, and your error? What happens if we increase the position error constant? What happens to our error? If we make K sub P bigger, the error goes down. And how is K sub P influenced? What is that relative to our system? What is K sub P? That's just our DC gain, isn't it? So if we increase the DC gain of our system, we are improving our steady state error. We're decreasing the steady state error. In our case, for system A, we had tau naught equal to 1, K naught equal to 10, and the DC gain, or G of 0, is now 10. And what's our steady state air? We now have 1 over 1 plus k sub p, or 1 over 1 plus 10, and that's now 1 over 11, which maybe I don't like to think of 1 over 11, but I know that that's less than 1 over 10, and I can know what 1 over 10 is. That's a 10. So I have now a a steady state air less than a 10. What happens if we look at that for system B? System B had different values for k sub 0 and tau naught, or tau sub 0. In that one we had k sub 0 of 1 and tau naught of a 10. Now what's the steady state air for this system? Or what's the system type for this second system, or system B? What's its system type? How many integrators are there? How many poles at the origin in G? Don't have any pole at the origin, do we? In G, there's no S in the denominator that's factored out. So there's no pole at the origin. This is a type 0 system. It's the same type as our previous one. And this one now we want to worry about our DC gain in terms of assessing the steady state accuracy. This is now 1 over 1 plus k sub p. The formula is still the same. It's just now, do we have a different DC gain for this system? What's the DC gain of system B? We look at S as S goes to 0, and that's k naught. In this case, k naught was 1. And now what's our steady state air? 1/2. In the previous case, system A, it probably reaches something a little bit more than 0.9 when we wanted it to go to 1. And it had this exponential approach to 1, and it reached 0.9, a little bit more, because its air was less than 0.1. Now, our output is going to 1/2 when we wanted it to go to 1. Our air is 1/2. We didn't get nearly as close to our final value, our reference input in system B, and we had a larger air. So this was a system type 0, and it also had a finite air due to a constant input. Let's look at the third system that we had played with in previous lectures. And this one, I think, was system C. Here, G of S is 1 over S, S plus 1. No adjustable parameters in this, but what's the system type? Maybe I shouldn't say type, well, I just don't want you to confuse the type 1 with type 0, the 0 and the O. I could use the number 1. I thought you were putting a slash through my 0. That's a terrible one, but you won't tell my penmanship person that there's a type 1 system. Why is it type 1? We have that one pole at the origin in our system. And now let's look at our steady state air for this system. Air steady state is the limit as t goes to infinity of e of t, and we always have to have a stable closed loop system or the error won't even make any sense. If our system is unstable, we're not going to have an error. It's just going to go, our system will go off to infinity and we won't have an error with some reference input. But here we have a closed loop system that was stable. We can apply the final value theorem. And we now have the limit as s goes to 0 of s, 1 over 1 plus g of s, that's still the same, times our unit step, which is 1 over s. This s cancels that s, and let's see what we have if we start plugging in the particular structure for the plant g of s. The limit as s goes to 0 of 1 over 1 plus, and our plant was 1 over s, s plus 1. And that may get a little bit funny trying to make that evaluation, so let's try to clean that up a little bit so that it's easier to interpret. We now can get a common denominator downstairs. And what happens to the denominator and the denominator? That goes upstairs. It now goes into the numerator. And what happens as we let s go to 0? Do we get 0 over 0? No, we don't get something indeterminate. What happens in our denominator? We have 0 plus 1, so that's well behaved. Our denominator is well behaved as s goes to 0. That's a good thing. What happens in the numerator? It goes to 0. So now we have 0 over 1, and our steady state error is 0. The last time it was 0.1 or less and 1/2. And now we have it locked in. We're right on. We're tracking exactly whatever we put in. Question? Yes, so if you look at this, and that's what we're going to do, we're going to go close. So the question was, what if I just evaluated earlier on in my derivation, I think, in terms of what's the limit as s goes to 0 in this blue expression on the right in the middle of the screen. We now have 1 over 1 plus, and what's g of s doing as s goes to 0? It's going unbounded, so you have 1 over 1 plus infinity, which is equal to 0. Well, we're going, so is that fine to do on the test? As long as it's clear, you might then say, well, let's do it, how do I want to say this? Let's look at it a different way. Suppose that you now said something like, well, yeah, it's okay, but I would just say, go ahead and show underneath that the limit as s goes to 0 of g of s goes to infinity. And then you can say equals 0 for your error. And the reason we are getting that behavior is because of that pole at the origin. But we definitely need to have our closed loop system to be stable. And the more poles we put at the origin, the less stable our system is. So we're messing with the transient behavior, but we're improving the steady state accuracy. The integrator, or the pole at the origin, in our plant g of s helps drive the air to 0. We're essentially integrating that air signal, and integrating that air. Anytime you integrate something, what's happening maybe to the integrator? It wants to build up. And you're forcing your closed-loop system now to drive that air to 0. And this was a type 1 system. In our G of S. And the DC gain of S, or G of S, was unbounded, or not defined. It was going off to infinity. But a type 1 system says that we have 0 air steady state for a constant input. And what did we have with a type 0 system as far as its steady state air due to a constant? We had 0.1 or less, or 1/2, a finite value of an air when we had a type 0 system. So as we increase the system type, we improve our steady state air. And what we will see here is the DC gain of G of S, which was this 1 over S, S plus 1, was, let's say, undefined, or going off to infinity. But we also now, with a type 1 system, with a type 0 system, we defined our position air constant. With a type 0 system, we will define another air constant, which is our velocity air constant. And that's going to be helpful in just a minute. But the velocity air constant is this K sub B, which is the limit as S goes to 0 of S times G sub C of S, G of S. And in our example, what's the velocity air constant? We didn't have any G sub C, we had this. And what's that limit as S goes to 0? That S cancels that S. And now we let S go to 0. And we have 1. And that's now going to be important for the next property that we are going to start examining. For example, what happens if we apply a ramp input to these systems? What happened when we applied a constant input? With the type 0 system, we had a bounded air, didn't we? With the type 1 system, we had 0 air. Now we want to make the input a little bit more demanding. We want it to be a ramp input. And now we're asking what happens to a type 0 system, to our air signal. Can we track that ramp input? Remember when we were dealing with this robot welding? We actually were able to have some finite or bounded air between the reference input, this triangular or sawtooth waveform, and the actual output. Would that have happened if we had a type 0 system? So let's look at what happens for system A. Suppose we now have G of S of K sub 0, tau sub 0, S plus 1. And this is a type 0 system. Our air, E of S, hasn't changed in terms of our expression. That's 1 over 1 plus G of S R of S. But if we have a ramp, let's say now we do have it with a particular slope of A of t, what's R of S now. I now have A over S squared. So let's now look at what happens to our air when we have an input R of S of A over S squared. We have E of S is now this 1 over 1 plus K sub 0 over tau sub 0 S plus 1 times A over S squared. So I'm just looking for the air signal. I'm not trying to apply the final value to it. This now gives me what? Kind of a mess, but I can clean that up a little bit, can't I? I can get a common denominator downstairs, and the denominator in the denominator flips upstairs, so that I have A times tau sub 0 S plus 1 all over S squared tau sub 0 S plus 1 plus K sub 0. And if I wanted to, I could factor that into a pole 0 type form, and I could have tau sub 0 times S plus 1 plus K sub 0 over tau sub 0. And now I know where my pole is. It's at minus the quantity 1 plus K naught over tau naught. What's the expression for little e of t look like in the time domain? Do you know what pieces make that up? And by that I'm saying hint, hint, partial fraction expansion. What's the partial fraction expansion of E of S look like? My denominator is S squared times tau naught S plus a pole. Is that what I heard? So now if that's my partial fraction expansion, and if I've solved for these alphas, what's little e of t in terms of the alphas? What's e of t? If I inverse Laplace transform alpha 1 over s, and if you get that on a job interview, you better be able to inverse Laplace transform alpha 1 over s. That's just alpha 1, right? What's the next one? That's alpha 2 times t. And what's the last one? I just cleaned that up a little bit, didn't I? I just made sigma equal to 1 plus K sub 0 over tau sub 0. I wasn't showing my work. But I did after I wrote that down. I just jumped to the answer. But now what does that mean for my air signal? What's the air signal doing? If this is my reference was a ramp. What's the air? What's the air doing as a function of time? What's the middle term doing? The third term, what's it doing? It's going to 0, so we can forget that one in terms of if that's all we had, then our air would be 0 and we would be tracking that ramp. But we actually have a constant offset of alpha 1, but we also have this alpha sub 2 of t in our air, so our output, let me exaggerate it a little bit more. It can't catch up, can it? This is our y of t, and this is our air signal. And that's growing with time. That's growing as alpha sub 2t. So we can't catch up. We want to go here, and we just can't keep up. That's our difference, and that was a type 0 system. So the system is unable, this type 0 system is unable to track a ramp input. So that type 0 system had no ability to keep up with this reference input of a ramp. So if you put in that sawtooth wave pattern and you had a type 0 system, you wouldn't be able to do a very good job of welding. Yes? So can you tell that by looking at the roots of the Routh-Hurwitz? You really can't, because the root, well, it depends on what you're looking at. So in the Routh-Hurwitz, if you were looking at the poles of your closed loop denominator, those might be stable. It's just now that your system is, even though it's stable, it's trying to get there, but it can't keep up with what you're asking it to do. So the demands from your reference input signal are too much for this particular system type. Let's see what happens to our steady state air with our type 1 system. And this was system C, and it was a type 1 system. And we are using R of S of A over S squared, or as a ramp. Now we first have to have our closed loop system being stable, and it is. If it's not stable, we can't even talk about a steady state air or steady state accuracy. The expression for our air is still the same. That's 1 over 1 plus G times R of S. And in this case, our steady state air is the limit as S goes to 0 of S E of S. And that's the limit as S goes to 0 of S times 1 over 1 plus, let's say, G of S. Let's keep that in there for now. And this is A over S squared. But now what happens? This S cancels only one of those S's, right? And we now have A over the limit. And now if I distribute that S downstairs across the two terms downstairs, I have limit of S plus S G of S as S is going to 0. Is that clear? What happens to the first piece of that two-term denominator as S goes to 0? That goes to 0, and so I now have A over 0 plus the limit as S goes to 0 of S G of S. But what was that? Do you remember what that was? We defined that to be our velocity air constant, K sub V. That's the limit as S goes to 0 of S, and in our case, G of S was that, wasn't it? And this now goes to 1, so that our steady state air now is A over K sub V, which is 1, or our steady state air is A. And that's bounded. Now our system can keep up. We have a bounded air, but we're tracking our reference input. If we wanted to do better, we would throw another pole at the origin, and then we would have 0 air to that ramp. But now we would have two poles at the origin, and our system is much more difficult to stabilize. But these poles at the origin give us a good thing for steady state accuracy. They make it more difficult to worry about the transient or the stability of the system. But I hope that that's now been brought home from today's class.